Hi guys, we are still working with series here, and we are testing for when series converge and diverge. So we're looking at two tests today, the integral test and then the p-series test. Both are very useful tests. All right, so for the integral test, it's actually probably one of the harder ones to do because we have to check some conditions. First, we have to check, is the series always, or is the sequence inside always positive? Are all the terms of the series positive? If we wrote it as a function, would it be continuous? So we can't have any asymptotes or things like that. And is it always decreasing? Or decreasing after a certain point is okay? Like, so if it increases for like the first 5 terms and then decreases, that's okay too. Because then we could just write out the first 5 terms and then say the series is from, term 6 onward, and that's fine. But the series and the integral from 1 to infinity, or if we start at 1 here, will both converge or both diverge. So they will do the same thing. All right, so that's very useful. So here's our first guy. We have n over n squared plus 1. All right, so just looking at that, I don't know. If I took the limit to do the nth term test, I would get 0, which tells me nothing. So if I do the integral test, I would treat this like a function and say this is n over n squared plus 1, and we're going from 1 to infinity. So from 1 to b, and the limit as b goes to infinity, because we don't write those improper integrals, dn. All right, so our u would be the bottom, n squared plus 1. du would be 2n dn. So we'd put a 2 there and a 1/2 outside. So we're going to get 1/2 the integral of du over u. All right, so we're going to get 1/2 the natural log of the absolute value of u, which is just n squared plus 1, which is already always positive, so we don't have to worry about that. And we're going from 1 to b. So we get 1/2 the ln of b squared plus 1 minus 1/2 the ln of 2. So now we take the limit as b goes to infinity, and this part here will go to infinity. So that means this diverges, which then tells us that this guy also diverges. All right. What about the next one? All right, so I was bad. So I didn't check if it was positive, continuous, or decreasing. So it's always positive. So that's an easy thing to check. It's like n over n squared plus 1 is always greater than 0. That checks out. It's continuous. It doesn't have any problems. Like there's no problem areas with the bottom there. And is it decreasing? Well, the bottom keeps increasing faster than the top does. So yes, it will be decreasing because the bottom's increasing faster than the top is. So after a certain point, for sure, it will be decreasing. All right, so again, I should have checked those first. So this one, let's see, 1 over n squared plus 1 is always greater than 0. It is always continuous. And it is always decreasing because the bottom continues to get bigger and the top stays 1. So it is decreasing. So all of those things are met. So now we can look at the integral from 1 to b of 1 over n squared plus 1 dn, and the limit as b goes to infinity, right? Improper integrals. All right, this is arctan of n from 1 to b. So this is going to be arctan of b minus arctan of 1, and the limit as b goes to infinity. So the arctan of infinity is actually just pi over 2, and the arctan of 1 is pi over 4. So this is just pi over 4, and it converges. All right, we got an answer. So that means this guy also converges. All right, so that is how we do the integral test. Again, it is one of the longer tests we do. So we'll learn other tests that'll probably be a lot faster for both of these problems in the next section, just FYI. But we need these tests in order to derive the rules for those other sections, if that makes any sense. All right, the p-series. So I mentioned this in class the other day. P-series is just when we have 1, or any number over there works because we can pull a number out front, over n raised to the p, where p is any number, any real number. is called a p series. So like it'd be 1 plus 1 over 2 to the p plus 1 over 3 to the p plus 1 over 4 to the p and so on. All right, when p equals 1, it actually has a special name. It's called the harmonic series. So 1 over n is 1 plus a half plus a third plus a fourth plus a fifth, like all those 1 over every rational whole number there. All right, and this series actually, we'll find out in a second, but it does some interesting things. So the way the p series works, and we get this from the integral test. The integral test gives us these p series rules. So all these functions are positive, all of them are decreasing, all of them are continuous after 0, all of them, no problem. We all start at 1 here. So the integral test works, and it gives us these rules that if p is greater than 1, the series will converge. Like 1 over n squared, this is a p series, where p equals 2, which is greater than 1, therefore it converges. All right, and this is my work. I said that it's a p series. I said p equals 2, it's greater than 1, converges. All right, this one is also a p series. P equals 1, which is less than or equal to 1, which therefore diverges. All right, so right there, yep, less than or equal to 1, diverges. So this harmonic series diverges. It's just about the smallest series that still diverges, if that makes any sort of sense. Like if this exponent was 1.001, it would converge. All right, but 1 by itself diverges. It's no good. All right, and let's add some extra ones in here. So like we can simplify stuff too. Like we could have like n over n to the 4th like that. And we can say, oh, well, that's just, or actually maybe n squared over n to the 4th to actually have to simplify that. Well, then that would just be 1 over n to the 3.5, right? Because this is n to the half, this is n to the 4th. And then this is again a p series where p equals 3.5, which is greater than 1. So it converges. I started to write diverge, converges. Big P, converge. All right, means that this is raised to a big power down here, and it gets really small really fast, where this one over here doesn't get really small fast enough. All right, so there's the integral test, and there's the p series test. Told you they were going to be short.